Hello, everyone. This is Professor Felipe Rodriguez again, and today we're going to be talking about queuing theory and queuing systems and how it applies to operations management. So I'm Professor Felipe Rodriguez from King's University College, MOS 3330, Operations Management, and within the idea of process improvement, we're going to be seeing queuing processes. So as usual, send me an email if you have any questions. Professor Felipe Rodriguez from the School of Management, Economics and Mathematics from King's University College, here, Western University, Canada. So, what is it that we need to read when we're going to be talking about queuing theory? In particular, this is very important from a operations perspective. Okay, let me hide this thing. Oh yeah, much better now. So I would recommend that you read chapter 16 from Cashon. So far we've read from chapters 1 to 5, and now I'm jumping to chapter 16 because I feel like this is a natural extension of what we're seeing. So far we've seen processes where we're dealing with average process times and average flow rates, but we're treating them as something quite fixed. So if I say the flow rate is 4, um, if the if the tech time is 4 minutes per client, if I'm talking about, for example, if the cycle time is 5 minutes per client, all of these things, we're treating them as very fixed. And now we're going to introduce variability in the process. And that's where queuing processes really excel. So chapter 16 from Cashon. I would also recommend you take a look at the note on queuing models from Professor Rasha Kashev and myself. This is published at Ivy Cases. Here's the product number, and here's the link. I strongly recommend you get it. And I would also recommend that you take a look at this. So this book is called Factory Physics. Factory Physics by Hopp and Spearman. So I'm gonna write down over here, Factory Physics by Hopp and Spearman. Really good book. Strongly recommend you take a look at that. Okay, sorry I couldn't show the book because of my background. Anyway, so what are our learning objectives today? First and foremost, what happens if I have a demand that is higher than my service? That is a big deal. Those are what we call unstable systems, or they haven't reached a steady state. So we can take a look at a little bit of that, how we usually call those as a transient state queue. Then we're going to look into queues with variable interarrival and process times using a single server. Then we're going to go into multiple servers and all the different performance measures that they take. And ultimately, we're going to try to figure out the role of economics of scale, pooling, and costs involved in queuing. So remember, we're trying to match our supply with demand. So tect and cycle, right? With the 3 P's, people, planet, and profit. So we have to be sustainable. Also, the idea that my operations would be very different if I try to differentiate myself in terms of my products or services, or if I try to be a cost leader in my market, right? If I cannot manage, I can if I cannot manage, I cannot measure. Sorry, apologize. It's already 3 in the morning. So anyway, you cannot manage what you cannot measure. So the idea that now with queuing systems, we can measure a few things. For example, the time in queue, the inventory in queue, utilization rate, and all sorts of different measures over here. And the process triangle as it relates to Little's law, right? So Little's law says that inventory equals flow rate times flow time. And when we look at the process triangle, like we had before, here's utilization capacity, here's variability, here's inventory, right? Basically, what has become the focus of our attention for this lecture is the idea of introducing variability in our processes. And we're going to be seeing that as variability increases, inventory tends to increase as well. And I'm going to show you mathematically how we do that. So excess inventory becomes waste. Excess capacity leads to unbalanced utilization, and variability becomes excess variability, right? So we're always trying to improve our processes. So continuous improvement through those improvement cycles like PDCA, right? DMake, and whatnot. We're going to be seeing a lot more of that when we see quality management and lean operations. And very, very important, operations and finance are linked together. And as I said before, I'm going to focus a little bit more in terms of COGS and the role that operations has in reducing COGS. So if you reduce COGS, you will have a higher margin. So let's look at this very simple process that that we are seeing right now. Okay, so the idea here is we have customers arriving because there is some randomness in arrival. There may be some queue forming over here, and then there's a process here. In this case, they're renting skis and snowboards to skiers, right? So that's the example that we have today. So what is it that we're looking for specifically? Oh, sorry, I did something strange over here. I apologize. How do I go back? Hide floating control. How do I hide this bar? I want to hide this bar. There you go. Nope. Excellent. So where were we? Over here. Right. So flow process for the ski butternut. So the idea is customers are arriving. They're gonna arrive at a certain rate. We're gonna call this A or even R. And we're going to be seeing the difference between these two terms very shortly. And then they're going to be processed at a certain process time P, or what we know from before, a certain capacity C, right? Why don't I do a little cleanup right now, and I start introducing a few aspects right now. So the flow rate, we know what the flow rate is. I'm going to say the flow rate is 1 over interarrival time, and I'll explain this very shortly. And capacity is 1 over processing time. All right. Now, what we need to look at these things is that what if I have a system that has a bigger demand than capacity? What happens to this system? So in other words, if I have a little chart over here, this is time, okay? And this over here is number of arrivals. What I'm saying is that the arrivals are growing over time. And if the arrivals are growing over time, but my processing time, or my capacity. In this case, if I use the number of arrivals, I'm going to say that this is my capacity. What if my capacity is constant over time? What do we expect to happen to the system, right? We expect the system to have more and more people coming, and as time goes by, these people will not be processed and they're going to start accumulating. So what we will see is as time goes by, the size of the queue or the wait time, so this could be a wait time in the queue, let's call this QT, or a size of the queue, let's call this inventory in queue. All of these things are gonna just grow and grow and grow, and they're gonna blow up, right? So this is what we call a busy period. So when demand exceeds supply, what will be the length of the queue? So the length of the queue, this is going to explode. This will only grow and grow and grow. So, but you can measure the length of the queue at a certain amounts of time, right? How long does a customer have to wait to be serviced? So because you can look at how that queue grows over time, you can make those kinds of predictions, and you can always figure out what the average time that those customers will predict. Now, very important, when demand exceeds supply, in queuing we call this busy, sorry, let me erase this. What am I saying? Not busy period. We're going to be calling this a transient state queue, right? So for a moment, capacity is higher. For a period of time, capacity is lower than your demand, so you just see things exploding. So here's the example. If I'm looking at the x-axis, this is time in minutes as time goes by, and I can observe the length of the queue as it grows up. I can say, for example, my processing time, the queue growth rate will be my demand minus my capacity. Demand, in this case, D, is greater than C. So my demand is greater than my capacity. So it should be intuitive that if my demand is, for example, 1.5 customers per minute, and my capacity is 1.25 customers per minute, at each minute that we go through, what will happen? 0.25 customers will join the queue, right? So here's the little process going on right now. Minute one, so 1.5 customers arrive, and I can process 1.25. In the next minute, another 1.5 customer will arrive, and I can process 1.25. But here there are 3 people, and I only did 2.5 people there, so I'm accumulating half a person within that interval of time, right? So every minute, 0.25 customers will be joining that queue. So can I calculate the time to serve those customers? Well, yeah, busy periods will occur. Time may vary over time. You don't really know when peak or busy times are going to happen, but you know what the capacity of the system is. You can calculate the utilization, and you can notice how much randomness you have in both the arrivals and in the service times. Okay? So why don't we look at this little equation here, time to serve customers. So the formula would be the time will be whatever time t you're looking for in this situation. So if I arrive at time 5, for example, at time 5, the demand divided by my capacity, this is the growth ratio, right? So if I go back to that chart that kind of goes like this is how much I'm growing. That is the slope of that growth, right? So demand being higher than capacity means that demand divided by capacity minus 1, this number is always greater than 1. So at time t, and given time t5, for example, I can calculate how long it would take to service that customer, right? And the same thing is, instead of looking from the perspective of how long it would take to service one customer at when that customer arrives at a certain moment in time, right? So for example, you arrive over here, if this is time, let's call this time 1, if that customer arrives over here, I might want to think in terms of when will be the time to service the queueth person in the queue. So your customer is complaining, oh, I've been waiting here for too long. When am I going to be serviced? Well, little formula, Q divided by capacity, right? So let's look at what this little example that we have here, the time to service the car arriving at 9 a.m. So if you open at 6 and 10,000 cars per hour arrive at the toll plaza at the bridge, but I can only process 8,000 cars, that's a clear case where the demand of 10,000 is greater than the capacity, which is 8,000 cars. Always remember, this is cars. Is that per hour? Yeah, right. So what are we going to do? Well, a car that arrives at 9 a.m. So we can see from 6 to 9 a.m. that's 3 hours. So the time is 3 hours. 10 minus 10,000 cars per hour divided by 8,000 cars per hour. All of that minus 1. When you multiply all those, a car that arrives at 9 a.m. will wait approximately 0.75 hours. So this is very useful when you're dealing with situations such as the demand is greater than the capacity for a certain moment of time. Can you figure out the performance of that system? All right. So, okay. So we saw at first how to figure out the time to how long a certain customer will wait given their arrival time, and how long it would take to service a certain customer within the queue. Now we can figure out what is the average waiting time uh, for that system that is in a transient state. And the formula is quite simple. It's literally what we had from before, but this is multiplied by half, right? So the idea here is the duration of that busy period, right? And that's going to grow, and then eventually it's going to drop. So this is the duration of that busy period. And the growth of the queue, this is this demand divided by capacity over here. So let's just call this number of people or the time. Right? So we're doing this in half. Maybe, just maybe, we're looking at this because this is a triangle, right? So we're looking at the area under the curve that allows for um, the average time. So it will be half of that area, right? So half times t times demand divided by capacity, all of that minus 1. So how do we do when you are in a transient state such as the one that we just described before? Do I reduce demand or do I increase capacity? So a lot of times one is easier than the other, right? So increasing capacity, maybe you need to hire overtime or extra workers to deal with your excess demand for a short moment of time. Maybe what you got to do is spread your demand apart a little bit. So one way of that is what we call peak loading pricing. So peak loading pricing happens a great deal. For example, flights that are very, very busy and you have excess demand for flights, for example, very early in the morning and very late in the evening. So you increase the price of those flights in order to reduce the demand, and eventually that demand is going to spread out through flights on the other time slots available, right? So most likely, for example, tourists and people that don't have a necessarily a time to need to arrive at a certain time at their destinations, they would be willing to forego those early morning and late afternoon flights for a cheaper price, right? Or you can offer off-peak discount. So reduce the price of your goods or the price of your service when it's off peak. So that's the idea of those 4 p.m. dinners, right? Uh, so what are you doing? By offering a 4 p.m. dinner, part of the demand that you would have for dinner at your restaurant would actually be shifted to an earlier time slot, therefore maintaining demand and capacity at relatively stable levels, right? Another interesting way is to think in terms of pre-processing, right? So maybe there are steps that you can take in advance to speed up your process and therefore allow you to better manage your excess demand. So, for example, in the automotive industry, there's this thing called CKD. So those are basically kits, and they're pre-assembled, right? So that speeds up the processing time. In this case, the assembly of a car. For example, we also may want to have, if you want to go to a drive-through nowadays, you can order online via an app. So that speed ups the process as you go through the drive-through because your order will already be done. So drive-through. So there's a lot of things that you can do. Another example is blood donations. Instead of walking in to donate blood and fulfilling all these forms and questionnaires, maybe you go online and you answer those questionnaires online, and then you arrive at the blood donation clinic and you don't have to spend so much time there waiting because the process time has been decreased by pre-processing done before. So now let's look at queues when the demand and service rates are variable, one server. And what I mean by this is that we have reached a steady state. This is a key word, and I'll be talking a little bit more about a steady state. What I mean by this is that the average arrival, so let's call this the inter-arrival time A, or even the flow rate R, okay, these guys are stable over time. They won't change. And the same thing will happen with your processing time. So your capacity or your processing time, okay, that those will be stable over time. So if I could put a little plot over here, for example, I receive 12 calls on average per hour, and I take 4 minutes to complete each call on average. So I might want to plot something like this. The arrival is, it goes up and down, but on average it's the same. So let's call this the flow rate. And here's the queue, here's the process. And if this is my capacity and this is time, I will also have relatively stable capacities over time. Okay, so in this one particular example, 12 calls on average per hour. This means 5 minutes in between calls. Okay, that is a big deal. That's what we call the inter-arrival time. 5 minutes in between calls or 12 calls per hour. Okay, so remember that flow rate versus some So flow rate is R, and the inverse of the flow rate, we will be talking things such as cycle times and whatnot, and tech times. Anyway, the idea here is 5 minutes in between calls on average. I can also have, if I know it takes 4 minutes to complete each call, therefore, this processing time that we have over here is about 4 minutes on average. It's going to go up and down a little bit. So remember this: if every call happens in intervals of 5 minutes from each other, exactly 5 minutes, and if I process every call exactly at with 4 minutes, one call will arrive. I will process that in 4 minutes. Then there still be another minute until the next call comes along. So the next call comes along at minute 5. I process that in 4 minutes. I'm idle for another minute, and then the next call comes along. So what happens? What happens if we add variability? What happens if we add randomness to the process? What if it's 5 minutes on average, but it could be 1, it could be 20, we don't know. What if it's 4 minutes processing time on average? So it could be 1 minute, but it could also be 10. When those two things start to happen, then we start seeing queues forming, right? So let's see how that looks a little bit more. So some of the terms that I mentioned before, the arrival process. So this is the flow of customers or units or parts or calls or patients, whatever flow unit you decide arriving to the system. And then you have a service process. This is the flow of customers or the flow units that are being serviced. Okay, so what you have is the arrival follows a rate R and the process follows a capacity C, right? And this is a rate of units per time, and capacity, as we've seen before, is units per time. However, the inter-arrival time is, we can measure that as A, let's call that A, inter-arrival time, and this is measured in times between units. And the processing time, we can call that P, and that will be the time that it takes per unit. So just so we remember, R equals to 1 over A, and capacity equals 1 over P, okay? That's the relationship that you flip one to get the other one. So I mentioned that we're introducing variability in the process. So let's look at variability with a little bit more detail. Look at this blue line where on the x-axis I have the number of observations. For example, each one of the customers as the order in which they arrived in my system. Okay, so the blue line is showing the inter-arrival time between these customers. So this guy took 90 seconds from the one to the previous. This guy took 100, and it's going up and down, up and down. But the blue line, if you take an average of the blue line, that average is around 100. All right. Now let's look at the red line. It seems to be very fast. The inter-arrival time is very, very fast, right? So it's taking 10 seconds, 5 seconds, 0 seconds, 30 seconds, 40 seconds seems to be the most. But if I draw a line here on average, that average will be at around 10. Now, all these, the blue process is fast, and sorry. Oh, I apologize. Oh my God, I'm going crazy. So sorry about that. So the blue process is in fact quite slow. The arrivals take on average 100 seconds in between, and the red process is super, super fast. Okay, so customers take on average 10 seconds in between each other. Now, let's see the amount of variation that we have with respect to the mean, right? So when we look into this, we have to think, well, okay, so variation over the mean. So that's the idea that perhaps I can divide a measurement of variation, for example, the standard deviation. And what if I divide that by the mean of a certain process, either the arrival time or the processing time, right? Then the blue line varies a lot. It's very slow, seems to be varying a lot, but with respect to the mean, it actually is not varying much, right? And the red line is a fast service, but it seems to vary a lot. So that ratio of variation with respect to the average is much greater. So even though the red line is fast, the inter-arrival times vary a great deal. And the blue line is relatively slow. It's a low demand process, but it has much less variance, right? So we can use that. And the ratio of the standard deviation to the average, like I showed before. So sigma A divided by A, or sigma P divided by P. So it can be the ratio of the standard deviation to the average inter-arrival time, or the ratio of the standard deviation with the average processing time. So in general, that's how we would go about the coefficient of variation of A and the coefficient of variation of P. Now, very important, let's get some intuition about this. If the coefficient of variation of any one of these two, it doesn't matter, goes up, meaning there's more randomness to the arrival process or to the service process, it is more likely that you're going to get perhaps 2, 3 clients arriving very fast in between themselves, almost at the same time, while you have a process that may be taking longer. So you start to accumulate queues by having more variation. So it should be relatively intuitive that as the coefficient of variation grows, that means that you may have 1, 2, 3 arrivals arriving very fast in this queue, while the process time over here, it's taking way too long, right? And then a new arrival comes in. So, and then it takes a long time, and then this process takes a short time. The more variability you have in the process, you will tend to have either higher inventory, right? And you have a lot of time waiting in queue, or a lot of time waiting in inventory as a working process inventory. So here's a few examples. Call center transactions, right? So it tends to be a relatively low coefficient variation, and maybe that's because there's a little bit of automation, there's predictability in the process, right? So you have a relatively low variation in the process. However, for example, when you have arrivals in batches, so for example, one bus full of customers arriving, or one airplane full of customers arriving, right? So there's a lot of variation in the process. Things are going way up and down, the coefficient of variation being really high. That's a system that becomes quite unpredictable. And the excess variation will lead to high inventory. So if we look into the process triangle, This is variation. This is inventory. As variation go up, inventory will also go up, right? So that's what's happening right there. And I left this middle one for last. For example, arrivals to the emergency room. This is a textbook example of what we call a exponential interarrival time, exponential A. And in this particular case, the coefficient of variation equals 1. That leads to an exponential distribution. And I'll show you exactly what I mean by now. This is very, it's helpful mathematically because the formulas simplify a great deal. But if the coefficient of variation is 1, that means that the standard deviation and the average of your process are the same, right? So the standard deviation and the interarrival time are the same. So here's an example of what I'm talking about. Let's think in terms of rate. Okay, so here's a distribution called Poisson distribution. And let's look at Poisson distribution in terms of arrival rates. In the x-axis here, I have the number of arrivals, right? So I'm going to call this, I'm using mu over here. Let's just call this lambda for a moment, right? So this is the lambda, the number of arrivals. So for example, the student cafeteria. You might want to have something such as, and this is just an example, right? I picked a Poisson rate here. Not necessarily realistic at this moment in time, but at the cafeteria, a lot of students, a lot of the arrivals. So, for example, units per minute and units per time. So, students arriving at the cafeteria, they often arrive by themselves, right? Um, Sometimes they arrive in pairs. That's quite common too, but it's relatively rare that you have a arrival rate of 6 students all at the same time within a minute, give or take, right? So 1 student a minute is fine, 2 students a minute is fine. It happens a great deal, but as you increase this, it becomes less likely, right? Here's another example. So this is not necessarily the cafeteria. This might be like a concert, right? Where you're observing the average here at around 10, okay? This guy, the average was around 2, all right? So in a concert, you're going to be seeing lots and lots of arrivals at around 10 people per minute, for example, or this could even be like an airport. This could be a toll booth in a highway, but it's going to be relatively rare that you're going to be seeing 20 people arriving per minute. At the same time, it'll be rare, very rare that you're going to be seeing 1 person arriving per minute. So this is a way that you can observe the distribution of arrivals. All right. Now the funny thing is the Poisson arrival rate. As we've seen before, rate equals 1 over a, right? So if you flip the Poisson arrival rate, you end up with exponential inter-arrival times. So in this case here, lambda, the average is 2. And in this case over here, the average is 10. So it's more likely, for example, on average, students will arrive at the cafeteria at a rate every every half a second, every half a minute, for example, right? And it would be unlikely that would take a long time in between those arrivals, right? And very, very likely that it would take a short period of time. And that is balanced by what happens over here at this long tail. And it's the same thing over here. Now, Poisson arrivals lead to exponential inter-arrival times. And as usual, as I said before, in this case, A is equals to your standard deviation sigma, or if this were processing times, they would have the same value. All right. So this is really important for us to consider because it leads to very neat mathematical formulas. I'm going to show you some approximation formulas to simplify things, but there are closed form solutions around the exponential interarrival times and exponential processing times. Oh, sorry, I did something stupid again. Let me hide. Oh, no. There we go. Sorry. So moving on. So here's the idea. Exponential interarrival processes, they're oftentimes they're very helpful, and they're called memoryless systems. And I'll give you quick example. These are callers coming into this call center, okay? This could be patients coming into a hospital. This could be cars in a toll booth. This could be apps in the processor of your phone. This could be opening files in your while they're being processed in your computer. The idea is this first guy arriving over here, let's call this dude A. As that person arrives into the system, that person will be processed, right, at a certain rate on average P. Now, if a second customer arrives, or a second call arrives into this call center, that arrival of this person B most often can be independent from the arrival of person A. So in the case of the student cafeteria, maybe they're not quite that independent because you're looking, for example, certain classes and at the same times and whatnot. But a lot of times you will find processes in which the arrivals are identically independent and identically distributed, meaning they're independent from each other. And what that allows us to do is to guarantee that this process follows a very stable mathematical behavior. And same thing with the processing time. Assume, for example, you are at the grocery store and you join a queue as you're waiting to go to the checkout, right? So the person immediately before you, that person arrived, and your arrival had nothing to do with the arrival of the person before you, and will have nothing to do with the arrival of the person immediately after you, right? And you're observing the cashier as the cashier works, and you're thinking, well, oh my God, I've been waiting here for a long time, and what will tend to happen as I wait longer, I'm going to get impatient. But my intuition would say that the more time I wait in a queue, the less remaining time will be for me to stay in that queue. Meaning, the longer I wait, my intuition as a human being would say the less time I'm going to be waiting until I'm eventually about to be serviced, right? So, other way of seeing this is when I go into a restaurant and I've been waiting for a table for a long time, I expect that most of my wait time is already done, is already over, and I'm just about to be serviced. But here's the deal. The inter-arrival is independent, but the processing time is also independent. So if you're at the grocery store, who knows? Person A might have a whole bunch of coupons and might have a whole bunch of price matching and might know the cashier personally. And then that processing time, even though on average it's a fixed value, will be a very long time. Therefore, the system can be memoryless with respect to the arrivals. It does not matter one arrival from the other. They're not dependent from each other. They're independent. So the state of the system does not matter on the previous state of the system. In other words, being processed right here will not be, the processing time will not be faster or slower because the previous customer was processed fast or slower. The system is memoryless. The state of the system does not define the state of the system in the next period of time. So if you already waited a certain time in queue, okay, so let's assume that the timing queue, let's just say on average it's 5 minutes. This is what you expect to wait at that queue. Because of the memoryless property of the exponential distribution for interarrival times and processing times, if you've already waited 5 minutes, your gut intuition would say, I have 0 minutes left to wait. I should be serviced right now. But the memoryless property would say, wait, what? You waited 5 minutes already? How much more time do you still have to wait? You still have to wait 5 minutes. That's the memoryless of the system. And this one particular example, so just recapping, if you already waited the expected wait time for a system, how much more will you wait? If you have exponential interarrival times and exponential processing times, you will, regardless of how much you waited, on average, you will still wait the average wait time. This is a classic system that we call, it's a memoryless arrival, okay, with a memoryless process and with a one server or a MM1. So let's look at that notation a little bit more. Here's what we call the Kendall notation of queuing. So the arrival, so it's always A slash arrival slash process slash number of servers slash number of places in the system slash the size of the population slash the queuing discipline. So the example I gave before was a MM1 system. I can extend that a little bit more. So for example, a MM1 system with an so memoryless or exponential interarrival times, memoryless process time, one server with, sorry, with an infinite queue size from an infinite population in a first come, first in, first out discipline, right? And I could have a whole bunch of different kinds. So for example, there's the exponential kind we call M, there's Erlang, that's another type of distribution. There's a deterministic distribution, we call that the D, meaning it's a fixed amount of time. For example, a machine that always performs the process time in the same exact time, right? So, and then there's also what we call the general independent time, where if you don't really know what the shape of the distribution is, but you know what the mean is, and you know what the standard deviation is, you can use general distribution formulas, right? So let's go. A queuing model with a single server. So one server in a single queue with exponential arrivals, inter-arrival times, and exponential service processing times. This is the MM1 system, okay? So let's look at the performance of that system. How does that look? I have a certain flow rate R, which is the inverse of the inter-arrival time, right? So flow rate is customers per time or units per time, and interarrival time is time in between units. Okay, let's keep that in mind. So I arrive into that system, there might be a queue. That queue, in terms of operations, we call that inventory. Oftentimes we call that working process inventory as well, right? And then that arrival waits a little bit, and B, and then is serviced. So there might also be an inventory in process at a certain process time P, right? And then you leave the system. Why is that important? In a flow of time, you enter the system, then you have a certain wait. That's a wait time. Let's call that time in queue or waiting time. And then you're going to be processed. That's the processing time P that we already know before. So your total time in the system, or what we used to call flow time, is now not only your process time, but also your time in queue. That is a key difference from the chapters that we were seeing before. We used to consider flow time as the processing time. Now, because we added variability to the process, randomness to the arrivals and randomness to the process times, now we have to include any possible time in queue, right? So nevertheless, because of Little's law, inventory equals flow rate times flow time. So now that we know about this, I can calculate, for example, inventory in queue being the flow rate times the time in queue, right? By using Little's law and understanding that inventory will be the flow rate times now the time in queue plus B, right? So we're going to be seeing that very shortly. So very important. When we're talking about queuing systems, we have to understand the concept of steady state. So as I said before, this is time and this is the interarrival time. We want this to be relatively stable, okay? It can change a little, but on average, it's stable over time. In the limit, as you go to infinity, this should be stable. And the same thing with the process time, this should be stable over time. That's what we call a steady state, right? Remember that for these models, processing time is always faster than the interarrival time. In other words, the utilization rate has to be less than 100%. In other words, my processing time has to be faster, than the interarrival time. Okay, so if the example of the call center, I process every call every 4 minutes, and each call comes every 5 minutes, right? So as long as my average processing time is less than my average interarrival time, I am in a steady state. If this happens the other way around, then we go into the system where we're in a transient state in a very busy period where demand is greater than capacity. We go to the previous formulas that we had before. So we can predict the time in queue, TQ, the time in service, and the total time in the system with a few very elegant formulas. So here's the first formula, again, for the M1 system, or if you add the coefficient of variation for the G1 system, the general arrival, general process with 1 queue. So the time in queue is your process time. So I'm going to single out this guy here. This is your first factor. The second factor is your utilization divided by 1 minus utilization. And the third factor is your coefficient of variation factor. So you're squaring the coefficient variation of the arrivals plus the square of the coefficient variation of the process time, all of that divided by 2. So the example that we had before, my process time was 4 minutes per call, and the interarrival time was 5 minutes per call, in between calls, and I had one server, so m equals 1. So p is 4 minutes. 4 divided by 5.8, 1 minus 0.8, all of that with a coefficient of variation of 1 and 1. This is equals to 16 minutes. Now, this is very important for us to realize. If the interarrival time were exactly 5 minutes and the processing time were exactly 4 minutes, the coefficient of variation would be 0. Okay? So 0 squared plus 0 squared, all of that divided by 2. That's going to zero this out. And anything from over here divided by 0, timing q would be 0, right? But because we have variation in the system, now I'm waiting on average 16 minutes. So it is very clear that from a decision-making process, from a operations manager, the coefficient of variation is one of the key drivers, right? That's where we should make decisions the most. With automation, with standardized procedures, right? With anyway, any kind of technology that reduces the coefficient of variation, right? So from Little's law, that's kind of nice. So Little's law, inventory equals flow rate times flow time. So now I can think in terms of inventory in Q. It's the flow rate times the time in Q. We know that flow rate equals 1 over A. So inventory in Q is equals to time in Q divided by A. And the same thing is inventory in process. I can also use Little's law. So what is the flow rate remains as R, right? So again, R equals to 1 divided by A. And now the flow time is the process in itself, the processing time in itself. So inventory in process is P divided by A, which, by the way, is your utilization rate. And your total inventory, I, is therefore the sum of inventory in Q plus your inventory in process, right? Or your inventory in Q plus your utilization, all right? So very simple formulas. Like I said before in Little's law, as long as you know one side, you can figure out the other. So it's very helpful to understand. So looking at the key drivers of waiting time, from that formula where we had P times utilization divided by 1 minus U times CV of A squared plus CV of B squared, all of that divided by 2. So this is my formula, right? This is time in Q. By the way, if you want to make this time in process, all you have to do is time in Q plus the processing time, right? Just remember that. So processing time, that's the capacity factor of the server. P is the processing time. So what happens to P? As P goes up, meaning my processing time becomes slower, the time in Q will grow. So fast service, small queues, slow service, queues will start to form, right? This makes sense in terms of intuition. If you can process people really, really fast, queues will not be formed, right? So think of the emergency room, for example. If you can treat patients really fast, people will not wait. Call center, if you can process calls really, really fast, then you don't have to worry about queues being formed. But there are more things that we can look into this, right? So the utilization factor is another one utilization divided by 1 minus utilization. So what happens here? What if my utilization goes up? By the way, inside utilization, what we have is P divided by A, right? Remember this. So, but looking at utilization as a whole, as the utilization goes up, what happens to the timing queue? So this thing, utilization going on. So this goes up and this goes up as well. So let's look at the denominator for a moment. As utilization goes up, this number approaches 1. So 1 minus something that in the limit approaches 1 will lead to a very, very, very small number. And anything divided by a very, 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 very small number will be a very, very large number, right? So in this one particular case, my upper bound is 1. So for example, if the utilization rate is 0.8, so it's 0.8 divided by 0.2 ultimately. If my utilization rate is 0.9, it's 0.9 divided by 0.10 and so forth. So as utilization goes up, the timing queue goes up a great deal, right? So the timing queue is very sensitive to utilization. In fact, if I could plot a chart, I'm even going to change the color of this guy right here so you guys can see what I mean. If this is utilization and this is timing queue, what happens is in the beginning, there's very little weight, and as your utilization increases, it just shoots up. So in other words, as your system becomes busier, a small change in the system will make a huge change in the wait time. So another thing that we must add to this analysis is the fact that the utilization rate has a limit of 1, right? Or 100%. So as you approach 100%, your queue just blows up, okay? And ultimately, the variability factor. So both of these coefficient of variations, as the coefficient of variation of both A and P go up, what happens is they are squared, right? So any small increase in the coefficient of variation increases the time in queue squared. That is why I like to point out the idea of variability. And if you look at the process triangle, variability increases your inventory, right? So as a decision maker, as a manager, variability should be one of the drivers that you should attack the most and fastest and give focus to this, right? Because any gains in reducing the variability, the squared factor over there will allow for a much smaller timing queue. And because of Little's law, again, remember Little's law, inventory equals flow rate times flow time. If we're talking about the timing queue, the inventory in queue, right? Any decreases in the timing queue will also decrease inventory. So there you go. Now let's look at when the demand and service rates are variable, but now we have multiple servers. So it's not a single server anymore, it's multiple servers. So nothing really changes from what we had before, but the fact that we have a single queue coming in, and now these customers may be serviced by different servers altogether. So the intuition would be if it's a single queue and multiple servers, maybe there are some gains to be made. You've likely been to a grocery store or to a pharmacy or to some kind of store where you have a single line feeding to multiple servers. We will understand why that may be a setup that makes a lot of sense, okay? So now utilization, number of servers, and stable queues. So using the same example from the textbook, the answer call center, now the utilization will change a little bit. Before we had P over A, now we have a number of servers. So what we have to do is divide the flow rate, same as before, this is your demand, by your capacity. But your capacity now, C, is the number of servers divided by P, right? So your utilization rate becomes P divided by A minus M. So this is important using the same example as we had before. Now, if we have 6 people in our call center, our processing time of 120 seconds, the inter-arrival time is 25 seconds, and the number of servers is 6. Now I have a utilization rate of 0.8 or 80%. Okay, so it doesn't change much. It's always demand divided by capacity, right? Now, in an unstable queue, like we were seeing before, this one example is showing that over time, the number of customers in the system is increasing. This is not a stable system. We need a steady state. So we need this behavior to be relatively stable over time. The average time must be relatively stable. Otherwise, the queue will just explode, like I was showed before. We gotta have this graph in our heads. I can never go over 100%, otherwise the queue just explodes, right? So this is what we need. We need a stable system over time. Now, what is the difference when you add the time, the number of servers in the formula? We get this really nice approximation formula. You can get a really good explanation for this approximation formula from the factory physics book by Hopp and Spearman. I strongly recommend you take a look at it. But we have three factors. So this first factor, we can call this a capacity factor, okay? Then we also have a second factor, like we had before. This is called the utilization factor. But I would like to notice this exponent right there. That's a big change. There's a square root of 2 times the number of servers plus 1. All of that minus 1. Okay? Why is this important? Well, if m equals 1, so 1 plus 1 is 2, 2 times 2 is 4, square root of 4 is 2 minus 1 equals 1. The formula reduces to the original MM1 system. So this formula, it works for the MM little m system, right? Or if you add the coefficient of variation, this becomes a GGM. Sometimes we call this a GGS system, okay? And thirdly, we have what we call the variability factor. And as we've seen before, these three terms play out the timing queue in a predictable manner, okay? So using Little's law, you can do the exact same kind of calculation, right? So inventory in queue remains TQ divided by A. Inventory in process remains P divided by A. So let's look at economies of scale and pooling. So how is it that I can assess economies of scale? What are the drivers of timing queue? So let's look at that formula again. So the formula is timing queue equals P divided by M times utilization square root of 2 times m plus 1, sorry, minus 1, all of that 1 minus u. And here now I have the coefficient of variation squared of a plus coefficient of variation of process squared, all of that divided by 2. So let's look at the capacity factor. The capacity factor is P divided by M. So when M increases, we can see from this formula as M goes up, the denominator becomes larger, therefore the timing Q goes down. Okay, same thing with the processing time. If the processing time goes up, because it's now in the numerator, then the time in Q goes up. So as we saw before, slow processes tend to form queues when there's variable demand and variable capacity. But now the number of servers decreases the time in queue. What is the intuition here? Go back to a store, go back to a grocery store, whatever. If you have more servers, the time in queue will go down. Here's another good example. Your computer has a quad-core processor. What is that doing? Instead of having one microprocessor, you have 4 microprocessors inside your computer working in parallel. So the more servers you have, the more processors you have in your computer, the faster your computer will be compared to having a single processor. So let's look at the utilization factor. So utilization factor is U square root of 2 times m plus 1, all of that minus 1 divided by 1 minus u. Okay, so remember that U equals P A times M, right? So, but let's keep U constant for a moment. And what I'm going to say is what happens if M goes up? So if M goes up, utilization rate will change, right? But look at that exponent right there. Let me change the color so we can take a greater detail to that exponent. There's a big fat square root over here. So as M increases, this number over here will increase, but at a slower rate because it's square rooted. So square rooted, right? And remember, the utilization is always less than 1. So this is always less than 1. So when you have an exponent on a number less than 1, what will happen is that this number becomes small, right? So as m increases, you will have the time in Q is going to be factored by some kind of square root. So the time in Q will go down. But very importantly, it will go down square rooted, meaning there are diminishing returns to scale. This is a key insight from this formula. If you have a call center, you have 50 servers, and then you double that, it does not mean that your time is gonna be halved, because there is this square root component there. So there are diminishing returns to scale. So just think about this from the intuition of demand. Once you have enough servers to fulfill your demand, adding extra servers does not help, right? So an interesting thing that you might want to think about is, wait a second, so what is that number of servers that we should be looking at? Well, what do we know about A? What do we know about P? And what do we know about M, right? So what is the number of servers M that I need to fulfill my demand, the minimum amount, to run this process? So think about the call center that we had before, where we had A equals, what was it? It was 12 callers per hour. So A was 4 minutes in between calls, and P was 5 minutes in between calls. So your number M of servers should be at least P divided by A. So this should be 5 divided by 4. So this number is a number that is greater than 1. So you can approximate that to 2. So you should have at least 2 servers in that system, right? If you are indeed, if you want to have a process that will be stable over time. Now let's look at the variability factor. Again, CVA squared plus CVP squared, all of that divided by 2, right? So as I said before, as you increase variability, the time in queue will also increase. But notice that now we're not square rooting anything. What we're doing over here is squared. So this grows by a lot, right? So those are the key intuitions that we have from this formula. Now, let's look at that graphically. On the x-axis, I have my utilization, and on the y-axis, I have the time in queue. So these are the shapes of utilization by time in queue when I have 6 servers, 12 servers, and 60 servers. And I want to point out that look at the system with 6 servers, how fast the queue grows. And I'm not even close to that 100%, and that queue this is gonna explode in the, right? As you approach the 100% mark, the timing queue will just grow and grow and grow. Now, look at what happens when you have 60 servers from 80% utilization all the way up to, say, 90, sometimes even 95% utilization. Your average wait time, the timing queue over here, is still very small. It's less than 10. Compare that with the 40, and then you go to 85, you're already at 75. You go to 90%, you're already at 120. You go to 95%, you're way above 200, right? So what that means is big systems, high capacity systems, right, perform better. In other words, there are economies of scale when you increase the number of servers in your system. All right, so that's a key takeaway that we can have from queuing. Bigger systems tend to perform better overall than smaller systems. If you don't have a lot of servers, any increase in utilization will lead to a big jump in the time in queue. And because of Little's law, I equals R times, so the inventory in queue is R times time in queue. And because of Little's law, small systems not only grow in average time in queue, but also in average inventory, work in process inventory. So economies of scale provide efficiency, and we can look at that from a pooling queue perspective. Let me give you an example. here is a grocery store. This could be any kind of system, right? Most of us can relate to the grocery store as an example. So I have 4 servers. Each one of these servers has its own queue, okay? So I have 4 parallel servers, and they're basically independent from each other. That's the idea. And I know that the interarrival time for each one of these systems is 100 seconds, okay, in between customers. And the processing time here is 90 seconds per customer, right? So what can I do with respect to this system? I know that each one of this system works independently, and so my M equals 1. So I can calculate several key performance indicators, and I'm going to start with the utilization rate. So the utilization rate for each one of these servers is P divided by A, right? So P divided by A. So that means 90 divided by 100. So the utilization here is 90%. So it's a pretty busy system. All of them are on average, 90% utilized. Now, what else can I do? Can I calculate the time in queue? Sure. So the time in queue, what would that be? So the time in queue in this case would be P times utilization 1 minus U, and coefficient of variance of A and of B. Let's assume this is 1 for now, right? So this is what we call a 4 times M 1 system, okay? So all the coefficient part, I'm going to leave it out. So this becomes 90 times 0.9 divided by 1 minus 0.9. So in the end, what we get from this guy, the time in queue will be 810 seconds. And I can calculate the inventory in queue also, because I can use Little's law. So the flow rate is 100 times what was that again? The flow rate is 100, and I know what my timing queue is. Oh, sorry, flow rate is not 100. Jesus Christ. The interarrival time is 100. Apologize. So 1 over 100 times 810 seconds. So what I get from this guy is that the inventory for each queue is 8.1 customers, right? Now the inventory in process is the utilization rate. So that's 0.9. So 0.9. So on average, each queue has a total inventory of 9 customers, right? So because I have 4 queues, so I have 36 customers on any given time on average in a steady state. That's the key point, on average. Sometimes it's going to be more, sometimes it's going to be less, but on average, it could be 36 customers. So let's record these numbers. These are really important. 810 seconds and 36 customers, right? So let's move to a system that is pooled. I have a single arrival. Now remember that before I had 4 queues arriving at 100 seconds each, right? So if I put these 4 together, that means that within 100 seconds, 4 customers will arrive. So now my arrival rate is 25. Okay, so I had 4 systems independent, with one customer arriving every 100 seconds. I put those together. Now I have 4 customers arriving every 100 seconds, which makes the interarrival time 25 seconds per customer. And P is still 90. Okay, what is it? What can we do? Utilization rate. What will be the utilization rate in this particular case? We now have 4 servers. So the utilization rate, the formula is a little bit different. It's not just P divided by A, it's P divided by A times M. So let's see what that makes. Processing time is the same, 90 seconds, right? A is 25, M equals 4. So in the end, my utilization rate is 2.9, it's still 90%. So both systems have the same utilization rate. I'm gonna circle this guy because this guy is really important. Now let's see if I can figure out the time in Q. So the time in Q will be P divided by M times that weird utilization component where I have this is squared 2 times M plus 1, all of that minus 1, right? And the CVs, I don't have to consider the CVs because the CV of A and P, I'm considering that 1. So this is what we call not a 4 times MM1 system. This is a MM4 system, right? So I can calculate this. So the time in Q is therefore 90 divided by 4. All of that times, so I know the utilization rate is 0.9 already, 0.9, 1 minus 0.9. And now this weird component over here, 2 times 4 plus 1, all of that stuff minus 1, okay? And so this will approximately, when I calculate these numbers, this will give me approximately 179 seconds. So I'm gonna circle this because this is really important for us. We had in the parallel system 810 seconds. Now we're down to 179 seconds. What did we do? We just pulled the system together. It's a single queue being serviced by 4 servers. So what is the inventory in Q? So this is TQ divided by A. So 179 divided by, what was that again? 25, right? So this gives me, so this is 179 such and such, blah, 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 blah. So this is approximately 7.16 if you run the numbers a little bit. So 7.16 customers in this system, right? I know the inventory in process, that is P divided by A. So P is 90, A is 25, so this gives me 3.6. So my total inventory in the system is 7.16 plus 3.6, these two guys, so I have 10.76 customers. This is my total inventory. So compare that to what we had before. That was 36 customers, 810 seconds, 36 customers with the same utilization rate. Okay, so ultimately, the pooled system performs much better with respect to time in queue, performs much better with respect to customers, to inventory in queue, from 10 to 36, give or take, right? while you have the same utilization rate. So that's a good example of the power of pooling right there. And to finish up, we're managers, right? So we have to make decisions, and oftentimes we have to put operations and um, finance together. So is there a cost of queuing? I'm going to show you that there is. So the in this graph right there, I'm showing you in the x-axis, this is the number of servers M. Okay, M number of servers. Let's just assume don't matter much about these numbers here on the right, but this is going to be cost. Okay, this is cost in dollars. So let's look at the cost of service. Let's call it cost of service CS. So what would that be? For example, this could be the wages that you pay for each one of your employees. So wages are constant. So if you pay, I don't know, $100,000 per year for one employee, what you're going to have is, if you have two employees, then it's $200,000 per year. If you have three employees, $300,000 per year. So this is this one line, blue line right here, right? It's constant. So let's call this CS, okay? It's increasing and linearly increasing. Okay, now let's look at the cost of weight. So what can you do with respect to the cost of weight? So I'm gonna call this CW right there, the cost of weight. So we know that the wait time, if this is utilization and this is time in queue, or this is inventory in queue, it doesn't really matter. Utilization goes up and it's non-linear, right? It's exponentially increasing. So it makes sense that as you reduce your utilization, in other words, you're increasing M, right? Remember, utilization is what? P divided by A times M. So as you increase M, utilization drops. So drops your cost of weight. So here's an interesting question. What is the cost of weight? Well, it could be hours not worked. If you're at the emergency room, the cost of wait, if you wait too long with a stroke, you may die. You may have irreversible damage, right? If it's a machine and the machine is waiting for repair, that will be the cost of waiting is the revenue that you did not generate by that machine being idle, right? So you can see that because the utilization uh, deals with the timing queue and the inventory queue in an exponential manner, then the cost of wait is decreasing, but it's non-linear. So this is the cost of weight, okay? Now, I can sum these two up together and call this a total cost. So let me just say, so my total cost will have to include the cost of service plus the cost of weight. Now, how can I go about doing this? Well, the total cost will be the cost of service. So what is, I can make those wages fixed, and I'm going to multiply this by the number of servers M. That's my total cost of service. Okay. Now, what about the cost of weight? Well, the cost of weight, here's an interesting part. So again, you need to multiply the cost of weight by the total time that people waited, right? So let's call this, for example, the time that people waited. Now, interestingly enough, one unit of inventory or one unit of your client or one unit or one patient, one client, one call, whatever it is that is your flow unit, one flow unit waited such time at a rate of this cost over here. Now, how many units within a certain time frame have gone through that? So you have to multiply this by your flow rate, which is, for example, if this is calls, so calls per year times the time that they waited times the cost of that wait. If this is patients, patients per year times the time they waited times the cost of that wait. If this is machines needing repair, so it's the same thing. It's number of machines needing repair per year times the time that each one of them waited times the cost. Wait a second. R times T from Little's law, this is inventory. So what you end up having, that is a big takeaway from this, is M times CS plus your average inventory times the cost of that weight. So your total cost right there is the number of servers you have times their salary. Interestingly enough, this is also called direct labor. This is part of COGS, right? And the cost of weight. Wait a second, inventory and the cost of weight, that is also part of COGS. That's your cost of inventory. So this is inventory. This is also part of COGS. So your total cost is, I'm not going to say it equal, but this relates to COGS. This relates to COGS, right? Now, as a manager, I'm just showing you right now that queuing is in fact COGS, and you gotta find a way to reduce your COGS somehow. Notice that as you sum up these two lines together, you end up with a convex curve right here of total cost, right? So if you go back to your microeconomics and if you go back to your calculus, any convex curve like this can be optimized. So you can optimize your total cost. In this particular case, it's you're minimizing your COGS by choosing the number of servers M, your direct labor or your direct resources, right? How is it that you do that? Well, it's your total cost. This is the derivative of your total cost with respect to M. This has to be equal to 0. Remember that? So you got to find that slope where the slope equals to 0. In this one particular case, where is that slope closer to 0? I think it's in between. Let's see. Anyway, it could be in between these two guys. I'm not necessarily sure, but I think it's this guy, right? Or no, it's this guy, in fact, right? So in this one particular example, this would be 4 servers. So what am I saying over here? I'm saying that there is a way that you can minimize your COGS, right? Or in other words, your inventory and your direct labor by choosing a optimal level of service. That is a big deal. So in other words, if you look at this green line, people are waiting. There is a cost of wait. You're not having a whole bunch of servers so they're idle and they don't wait too long, because that's going to be very expensive for you to pay all these people. The cost is too high. The same thing happens on the other way. If you have too little resources, too little manpower, this is going to go up, and too many people waiting, therefore your total cost is too high. So there is a optimum. Oh my god, this became super messy. Wait a second. Let me put this little derivative here someplace else. Apologize for that. Let me rewrite that derivative. So the total cost, the derivative of total cost with respect to m, this has to be equals to 0, right? So that's where the slope is equals to 0. So in other words, going back here, is your customers will wait. Your process will have work in process inventory. But what you will do is you're going to optimize your resources to minimize your COGS. So that is the big takeaway from queuing and costs. So in other words, to summarize, we have key factors: the capacity and the system, the utilization and the variation as they relate to the number of servers M, right? So they impact the total, the timing queue, and your inventory, in this case, working process inventory or total inventory for that matter. As utilization increases, the timing queue increases and increases at a faster and faster rate. So that's the chart I showed before, where as you approach 100% utilization, your timing queue starts to grow up a lot faster for the same measurement of time, right? So this guy versus this guy, right? So the utilization increases, therefore the timing queue and the inventory will increase at a faster and faster rate. And ultimately, the total cost of a system includes the cost of service and the cost of wait. In other words, the cost of inventory. And this relates with finance to COGS. So if you know how to work with queues, you know how to reduce the cost of goods sold in your company. And therefore, that's what I had for today. Thank you very much for this lecture. I hope you enjoyed it. I know it's kind of long and a lot of equations there, but it's extremely, extremely helpful. If you have any questions, please let me know. Write me an email or a comment below. So with that, I'm going to say good night, and we are done.